So Jai Hind everyone. So myself Ritesh Sharma. I am from Ajay Kumar Engineering College, Ghaziabad, and my department is Electrical and Electronics Engineering. So today I am going to discuss one important topics of the basic electrical engineering. That is from unit 1 is called the network theorem. In this particular topic or unit, the two important theorems are, we all know that, the Thevenin theorem and the Norton theorems. So we will discuss these two theorems, Thevenin's theorems and Norton's theorem, because these theorems are very important as far as the analysis of circuit is there. Whenever we found the current in any branch or the voltage in any branch, so these two theorems help us very much to solve the network. Okay, so first of all, we will take the Thevenin theorems, and then we will take the Norton theorems. Apart from the Thevenin theorem, we all know that there are some other theorems like superposition theorem is there. Okay, the theorem which is called the nodal analysis is there, KVL, KCL are there. So, but I have opted these Thevenin theorems and the Norton theorems because they are very important actually to solve any complex network. So if we look into the statement of this Thevenin's theorem, the statement is saying that in any combination of linear bilateral circuit elements and the active sources, regardless of connection and complexity, means in any circuit which is quite a complex or difficult circuit, we can solve this by using these theorems. In these theorems, in which the load RL may be replaced by a simple two-terminal network, in which the load RL, in which we have to find the value of current or the voltage, they are replaced by a simple two-terminal network actually. Two-terminal network. I will show you later how. Consisting of single voltage source, it having only a single voltage source and a series resistance. And single voltage source, we call it the VTH, called the Thevenin voltage, and the single resistance, which call it R equivalent, in series with the voltage source. So across the two terminal of the RL. Okay. This voltage VTH, which is called the Thevenin voltage, it is an open circuit voltage measured by at the two terminals of interest, in which we are finding the current or the voltage at that 2 point of interest. With load resistance RL removed. Because when we take the 2 points, this load resistance that must be removed from the circuit, and those 2 points will be the point of called the two terminals of interest. This voltage is called the Thevenin equivalent voltage source, and the R equivalent is the equivalent resistance of the given network as viewed through the terminal RL is connected but with RL removed, and all the active sources are replaced by their internal resistance. So it simply means that when we are finding the equivalent circuit of this, or you can say that the Thevenin equivalent circuit, we have voltage VTH and RTH. So VTH can be determined at these 2 points of interest, and similarly the RTH can be calculated by replacing all the sources, maybe the current source and voltage source, with their internal resistance. Okay, that is, the active sources are replaced by their internal resistance. Or if suppose the internal resistance is not given to us, we can take it as suppose in case of voltage source, they are short circuited and the current sources are open circuited, because their internal resistances of the ideal voltage and current sources are 0 and infinite respectively. Now let us understand the Thevenin theorem first more. So suppose that if it is in a given circuit, it is given that in this circuit, suppose that we have to find, this is the load resistance RL is there, and we have to find the value of current through this RL actually. Okay. Now this whole circuit, suppose it is given to us, it is in which we have the voltage source and the current source along with some passive elements here. Suppose R1, R2 and R3 is there. Now this whole circuit can be replaced by a Thevenin equivalent circuit diagram, in which we have the voltage source and a series resistance, which is called the RTH. It is also called This is called the RTH. And the load resistance which is connected across the point A and B. So this is the equivalent Thevenin equivalent circuit. And when we connect the load resistance through A and B, you can see that a complex circuit can be replaced by a simple circuit. Now let us take how we can understand how can we find the value of VTH and RTH. So for the calculation of the this R equivalent, which is also called the RTH, that I told you that all the sources are replaced by their internal resistance. So in this we have the voltage source and current source. So voltage source is short circuited and the current source is open circuited. Now if we find the R equivalent across this A and B point, we can find easily the resistance or equivalent resistance between the point A and B. That is called the R equivalent. And for VTH, we have to find the voltage across these 2 points AB. That is called the open circuit voltage. So open circuit voltage can be determined by just a voltage across these resistance, or you can determine by any technique. We can use the KVL, we can use the KCL, and we have to find the voltage across this A and B. That is called. At last, when we have to find the value of load current, actually, the load current in this particular, we have seen that the value of IL, you can see that the value of IL, you can write that is given by the VTH divided by the sum of the these two resistance called RTH plus RL. So this is called the current through this load resistance which we have to determine. So this is called the load current, or the current through the which we have to find the through the resistance. So with the help of this theorem, the current through any branch of the circuit can be obtained, treating that branch as a load resistance. So if we have to find the current in any branch, we can treat it as a load resistance, and then we will just remove that branch and obtain the Thevenin equivalent across the two terminals of the branch. So this is how we can perform, or we can use this theorem with the help of this procedure. The important part is this, the Thevenin equivalent circuit, how we can determine the Thevenin equivalent circuit. Then this is very easy for us to determine the how can we find the value of current in any branches. Okay, so let us understand. So let us recall some steps of this Thevenin's theorem. The first step is to remove the branch resistance through which the current is to be calculated. The first of all is we have to remove the branch, okay, where we have to find the value of current. So we remove the branch. Second step, calculate the voltage across these. So when we remove the branch, we have to find the voltage across these 2 points. We call the open circuit voltage by using the any network simplification technique, and this is our VTH. Okay, this is step number 1. Step number 3, we have to find this equivalent resistance actually. And this equivalent resistance, whenever we find this equivalent resistance, that we know that we have to replace all our active sources, voltage or current sources, by their internal resistances. Or if they are not given, the voltage source can be replaced, the voltage source can be short circuited and the current source can be open circuited. Then we can easily calculate the effective resistance across these 2 points A and B. And the step number 4, draw the Thevenin, then we just draw the Thevenin equivalent circuit diagram, and then last we will calculate our load current, the current through which we have to find the value of current. So these are the steps which we can follow while determining or while calculating solving any network actually. Okay. Now this theorem is very important, and this having certain advantages, but it has also some limitations. Like first is it is not applicable to circuits consist of non-linear elements. So this theorem is not applicable where in a circuit we have some non-linear element. Okay, so it is not applicable. It is only applicable for linear circuits, rather you can say. It is not applicable to unilateral networks. So it is only for bilateral, sir. Okay, not for the diode and triode and all that, because they are unilateral elements. So it is only applicable for bilateral, not unilateral network. Third, it should not be magnetic. There should not be a magnetic coupling between the load and the circuit. Whenever we are solving the network, there should not be a magnetic coupling between the networks. Okay, so and the circuit to be replaced by the Thevenin's theorem. In the load side, there should not be a control source or controlled from some other part of the circuit. So it should be not be like it could control from other sources actually or other controlled sources. So these are certain limitations so that we have to take into keep in mind while solving the network. Now let us see one problem based on the Thevenin theorem. Suppose we have to given that solve circuit using the find the value of current through the 10 ohm resistance using the Thevenin's theorem. Means you have to find the value of current through this particular branch 10 ohm. Okay, so that means we have to consider this 10 ohm as a load resistance, or the load resistance is there. So suppose we can say that this is our A and B. The 2 points are there, A and B. We have to assume that because this is our load, and the first step is that we have to remove it. Okay, while solving this network. So first point is to find the Thevenin voltage, remove the resistor 10 ohm. We removed it. Take it as A and B is the 2 point, and we have to find the voltage across this A and B. So now it is open circuited. Now for finding the value of A and B, we have to find the, suppose if we are calculating the VAB, which is equal to open circuit voltage, which is equal to your Thevenin voltage actually. And this can be determined by simple using this to find the value of current through this branch. So this can be calculated by simple calculation of this. Suppose in this branch, because since it is the open circuited, so the current will be equal to, you can say that in this branch, current must be equal to, I must be equal to, the voltage is 9 and the resistance is 4. 3, since it is a series, the 1 plus 3 is 4. So 9 by 4. So 9 by 4 is the, you can say that the current 2.25 ampere actually. So now this, to find the voltage across the 3 ohm resistance, we have to find, this is the 4 ohm is the resistance, effective resistance, and you can say that the current is 2.25. We have just calculated 2.25 ampere actually. Okay, so that means the Thevenin voltage across the 3 ohm, because we have to find the voltage across this is equal to this VTH, and that must be equal to your I into R. This is the I, suppose I, and this is the resistance. So VTH must be equal to your AB, which is equal to I into R. So 2.25 into 3 will be equal to 6.75 volt. So this is our Thevenin voltage. So next we have to find this, the Thevenin, after this the Thevenin resistance or equivalent resistance. So whenever we find the equivalent resistance of this, we have to find see the from that side, and all the sources are replaced by their internal resistance. So there's a voltage source is a short circuited when, and from this you can say that 1 and 3 is in the parallel, which is the combination in series. So while calculating the RTH, you can see that this is the RTH, the 2 plus 1 and 3 is parallel. So ultimately it's a 2.75 ohm. So this Thevenin equivalent, now when we calculate the RTH and the VTH both, we can easily in the position to draw the our equivalent circuit or Thevenin equivalent circuit. So this is my equivalent circuit, this is my VTH 6.75, this is the RTH which is in series with the your voltage source, and it is a load resistance. This is that is what we have, which we have removed earlier, Okay, so ultimately you can calculate this current by simply by putting in the formula of VTH upon RTH plus RL. So VTH is given at 6.75 upon RTH plus RL. So your current will be equal to 0.529. This is the value of current in the circuit or through this load resistance RL having value of 10 ohm. So this is a small example to understand the concept of Thevenin theorem. So the next theorem which I'm going to discuss is the Norton's theorem. In the Norton's theorem, the statement is that in any circuit, it is also a theorem which is used to solve or to simplify the network in any difficult circuit. So it is again, it is a linear bilateral circuit and active sources. In the circuit, we have some linear elements, bilateral circuit element, and regardless of connection and complexities. Now, this connection may be replaced by a simple two-terminal network. So again, this is replaced. This complex circuit can be replaced by two-terminal having current source. You can see the current source and the equivalent resistance in parallel. So earlier in the case of Thevenin's, we have seen that there was a voltage source, and there was a resistance in series. But here there is a current source and the resistance in parallel. So whenever there is a load resistance, RL is there. So RL is there across the AB, and we have to find, suppose that we have to find the current in this branch RL through the Norton's theorem. Now what will we do? We have to just replace the whole circuit by this Norton equivalent circuit. So we have to find the IN and R equivalent. We also call it the Norton resistance. Okay. So let us first of all find this is the basic explanation of this Norton theorem. So it means that it converts the complex network into a simple network having a current source and a resistance in parallel. Now let us see that in how we do that, how to find the value of IN and how to find the value of RTH or R equivalent. So value of R equivalent or Rn is same as that we have done in our previous case of in the case of Thevenin's theorem, that is called R equivalent is also called Rn. It is called Norton equivalent, which is the same as the effective resistance which is viewed from the point A and B. Okay, point of interest or the terminals of interest. Now, important part is that how can we find the value of IN, that is called the Norton current. So the Norton current is a short circuit current. Basically, it is a short circuit current that can be calculated by any technique, any simplified technique, maybe of nodal equation or KVL, KCL, so that we can determine the value of current through that branch which we have short circuited. So suppose this is the A and B is a point where the load was connected and that load is removed and these 2 points are short circuited, and then we will calculate the current through this particular branch. Okay, so IN and Rn, the two things are very important that we can calculate. So these are the certain steps which is very important to understand how to solve any particular numerical or the problem based on the Norton. The first step is that to short the branch through which the current is to be calculated. So first of all, what we do, we just short the branch through which we have to calculate the current. So first we short it, we remove the resistance and then we short it. Second is to obtain the current through this short circuit branch using any simple simplification technique, and then we have to find the value of current through that branch which is called IN. In step 3, we have to calculate the equivalent resistance that we have already know how we can calculate the resistance as we have done in the case of Thevenin's theorem. Step 4, draw the Norton's equivalent across the terminal of interest. So then we draw the Norton equivalent circuit. We all know that this is the Norton equivalent circuit, and then we connect the load resistance through that. Okay, so then we calculate the load Norton equivalent, and then in step 5 we again connect the branch resistance, that is suppose it is RL, and then when we connect the branch resistance we can easily calculate the current through that branches. Suppose if the current is IL, so IL must be equal to how much, because we can use the current divided rule, and when we use the current divided rule, this must be equal to, if IN is the Norton current, the load current can be equal to, we have to find the value of current in the RL, so it must be equal to upon, or we can also write it's Rn plus Rn plus R, your R equivalent and RL. Same it is written over here, R equivalent upon R equivalent plus RL. So this is the load current through that particular branch, that is RL. Okay. So this was the how we can solve the network. Now let us take the example based on the Norton and then we will solve. Suppose that this is the problem, determine the current through the branch through the this AB means AB in a given circuit using the Norton theorem. So simply, first of all, the first step is to, we have to find this AB, that means it is your load resistance. So that means it is a load resistance, it is considered as a load. Then next step is to find the Norton current. To find the Norton current, we have to short that branch from A to B. We have it shorted and find this value of Norton current. And we know that when we short it, while finding the value of current, all the current will flow through it, because current always follow the minimum resistance path. So that means this is having a zero resistance, so all the current will flow like this. So it means that from this circuit, it will simplify like this. So the current source of 30 ampere, this is the 10 ohm resistance, again it will be shorted. So this IN will be equal to 30 ampere. Simply it is equal to 30 ampere. The whole 30 ampere is flowing through this branch actually, AB. So your Norton current will be equal to 30 ampere. Next step is to find the Norton resistance. That is how to find the Norton resistance. The Norton resistance is the same technique that we have calculated in the previous case. Rn will be equal to the value, replacing all the sources with their internal resistance. So we have one voltage source. Current source. The current source is replaced by its open circuited. It is open circuited, and when we calculate the resistance Rn, you can see that this resistance is given by the combination of this 3 and 1 in the parallel, which is in the series with 2, and which is in parallel with this 4. So ultimately you can calculate that this 4 in this is the 2 plus 2.75. So Rn will be equal to the Rn must be equal to the given by 4 in the parallel with 2.75. So the Norton resistance can be calculated like this. So in any problem, we just replace the sources by their internal resistance, and if they are not given, they just be voltage source or short circuited, current source or open circuited, and we simplify it. It's not a big job actually. So this is how we can proceed actually for Rn. Now next, the Norton equivalent circuit. The Norton equivalent circuit, we have the Norton current, Norton resistance, and the load resistance. So we have calculated all these things, Rn and In, and then with the help of formula, we will calculate this. So replacing all this, In is 30, Rn is 1.63 upon 1.63 plus 6, we will find that it will be equal to 6.409 ampere. So this is how we can calculate the value of load current with the help of Norton theorem. Okay. So since we all know that the Thevenin theorem is basically the equivalent circuit of the Thevenin is the voltage source, and in case of Norton theorem, the Norton equivalent is a current source network. So both these two are the dual of each other. Means we can determine the Norton equivalent with the help of Thevenin equivalent, and Thevenin equivalent with the help of Norton equivalent actually. Okay, because they both are dual of each other. So again, let us there's one problem that we can calculate to find the Thevenin equivalent of a given problem. So this is the circuit given to you. We have one current source, one voltage source, and these are some passive elements. Now we have to find the value of we have to find the Thevenin equivalent of this through the point A and B. So these are the A and B are the 2 points. So for that, first of all, we have to find the VTH across these 2 points A and B, which is called the VTH, and RTH through this point. So when we calculate the RTH, we know that For RTH, this is the current source, open circuited, voltage source short circuited, and your circuit will be like this. So 8, 4, 8. So 8, 4, and this 8 in series with the 5. So 5 plus 8, 4, 8 is in series. And ultimately it is equal to 4 ohm. So 4 ohm is the RTH when we view to this point A and B. Next, the VTH. VTH is open circuit across this terminal A and B. So when we find the VTH, you will see that the VTH is the voltage across the point A and B. Across the point A and B. To find the voltage VAB, that is the voltage, we have to find the value of this current. It is, suppose it is I3, this is I4. Okay, suppose. Now you can find this I3 must be equal to, from this mesh, you can say I3 will be equal to this ampere. So I3 is equal to 2 ampere. And if we apply the mesh in this circuit, this is equal to 25 I4, because 25, this is current is flowing in this mesh. So this plus this plus this. So 4, 8 plus 8, 16 plus 5 and plus 4. 25, 4 I3 like this, and 12 is the voltage source. So this is a simple the KVL equation or simple mesh equation. So from here I4 must be equal to, when we calculate this, because already I3 is given to us, we put I4 is equal to 0.8 ampere. So if we have the value of I4, so I4 is flowing like this. Okay, it is flowing like this. So I4, that is equal to 0.8 multiplied by 5. So VTH will be equal to, this VTH is equal to 5 into I4. So 5 is the resistance, I4 is the current. This is the drop across the point A and B is there, is equal to 4 volt. So 4 volt is the Thevenin voltage of this particular network. Then we calculate the, so this is the VTH and RTH. So you can simply draw the circuit like this. Resistance is given that this, and voltage source is this. So the resistance we have already calculated, 4 ohm, and this the voltage source is 4 volt across the point A and B. This is the Thevenin equivalent of this. Similarly, you can calculate the same circuit we can use for the Norton, and again for that we have to find the, since the Norton resistance will be same as the Thevenin resistance, only we have to find the IN, that is called the Norton current. And the Norton current, because since the AB is now in this case short circuited, when we short circuit the AB, the current will flow like this. Clear? So I1 is clear, 2 ampere. From this circuit, this network or this mesh, I1 is 2 ampere. And from this whole circuit or mesh, you can say that 20 I2, because this is the circuit like this, 8 plus 8 and 4. So 8 and 4, 20 I2 minus I4, because I4 is the current flowing in this direction, I4, and 12 is. So with this, it will be equal to I2, because I2 is a current flowing like this. So I short circuit I2 will be equal to, I short circuit is equal to 1 ampere. So it means that the current source is there, resistance, Norton resistance across the point A and B. So Norton resistance was 4 ohm and the Norton current is 1 ampere. This is the, we can say that this is the equivalent, or rather you can say that it's a Norton equivalent circuit of the circuit. So this is the basic about the Thevenin theorems and Norton theorems. Thank you so much.